right, welcome back. This is the next episode in our series on world models. This is episode 2, and I'm glad you're here. If you caught episode 1, you already know the big question driving this series. What if the way we've been building AI is fundamentally incomplete? And if you're brand new, no worries, I'll catch you up in a minute. You can jump in right here and everything will make sense. But first, I want you to try something. Close your eyes for a second. Picture a road. A winding road going left, then right, through green hills. Now imagine a car on that road, your car, and you are driving. You can feel the curve coming. You know to turn the wheel before you even see the bend. Open your eyes. You just did something extraordinary. You ran a simulation inside your head. You built a little world, populated it with objects, and predicted what would happen next. No one told you how to do that. Your brain just does it. In 2018, 2 researchers figured out how to make a computer do exactly that. They built an AI that could close its eyes, dream up a world, and practice driving inside its own imagination. When it woke up, it could drive for real. This is the paper that gave the entire field its name. This is World Models. Alright, so quick context for anyone joining us. In episode 1, we covered a landmark paper from 2016 by Lake, Ullman, Tenenbaum, and Geschman. Their argument was simple but powerful. AI systems, no matter how impressive their scores on benchmarks might be these days, are doing something fundamentally different from what humans' brains do. Machines are pattern matching. Humans are model building. We don't memorize millions of examples. We build little mental models of how the world works, and we use those models to learn fast, imagine new things, and adapt on the fly. They laid out a vision. Machines need internal models, mental simulations, and understanding of cause and effect. It was a beautiful argument, but it was mostly theoretical. It described what should exist, not how to build it. So 2 years later, David Ha at Google Brain and Jürgen Schmidhuber, one of the true pioneers of deep learning, published a paper that took that vision and made it real. They didn't just argue that AI needs a model of the world, they built one. And then they did something nobody had tried before. They trained an AI to learn entirely inside its own dreams. The paper is called simply World Models, and it's one of those rare works that defines an entire field. So let's break it down. Before we get into AI, let's start with your brain, because this paper starts there too. Think about the last time you walked into a room you'd never been in before. You opened the door and without any conscious effort, you instantly understood the layout. There's a table, chairs, a window. Gravity is pulling everything down. The door behind you is solid. If you throw a ball, it will arc through the air and land somewhere on the floor. You didn't calculate any of this. You just knew. Your brain had already built a little model of that room. Not a perfect model. You might be wrong about what's behind the cabinet or how heavy a book is, but a good enough model that you could navigate, predict, and act. Now here's the really wild part. When you go to sleep tonight and dream, your brain will generate entire worlds. People, places, conversations, physics. None of it is real. But your brain treats it as if it is. Your heart rate changes. Your emotions respond. You learn from it. Athletes who mentally rehearse a routine, visualizing every move without physically doing anything, also sort of do the same thing. But it actually improves their performance. So your brain can practice inside its own simulation. Now the authors of this paper, Ha and Schmidhuber, start with a quote from a systems theorist named J. Wright Forrester. He said, and I am paraphrasing here, "The image of the world we carry in our head is just a model. Nobody imagines the whole world. We have selected concepts and relationships, and we use those to represent reality." That's the core insight. Your brain doesn't store a perfect copy of the world. It stores a compressed sketch, just the important bits, and then it uses that sketch to predict, plan, and act incredibly fast. So the question this paper asks is, can we build an AI that does the same thing? Here is how they did it. The architecture is elegant, and I'm going to explain it using an analogy. Now imagine you're watching a friend describe your vacation. They are showing you photos on their phone. You are doing three things at once. First, your eyes are taking in each photo. What's in it? What matters? What you can ignore. Second, your memory is stringing the photos together into a story. Okay, they went to the beach, then the market, then dinner. And third, you're making small decisions. I should ask about the restaurant or let me swipe to the next photo. The AI in this paper has the same three parts. So part one is the eyes. They call it V for vision. Its job is to look at raw image, say a frame from a car racing video game, and compress it down into a tiny summary. Not the full image, just the essence. Where's the road? Where's the car? What's the curvature of the track? All of that gets squeezed into a little code, a string of about 32 numbers. Think of it like a really aggressive Instagram filter that strips away everything decorative and keeps only what matters for driving. The technical name for this is a variational autoencoder, or VAE. But here is all you need to know. It takes a big, messy image and turns it into a small, clean sketch. And amazingly, you can reverse the process. Take the sketch and reconstruct a blurry but recognizable version of the original image. The AI can see through this compressed lens, and the important stuff survives the compression. The second part is the memory. They call it M for memory. This is where the things get interesting. The memory doesn't just store what the eyes saw. It predicts what the eyes will see next. Given what just happened and what action the car just took, the memory guesses what the next compressed sketch will look like. Let me say that again because it's the key idea. So the memory is a prediction machine. It's always asking, based on everything so far, what's coming next? It's like that feeling when you are watching a movie and you can sense the jump scare coming. Your brain is running ahead of the screen, predicting what will happen next. That's what M does, but with math. It builds a probability map of the future, not one fixed prediction, but a spread of possibilities. The third part is the decision maker. They call it C for controller. And here's the surprise. It's tiny, almost absurdly tiny. While the eyes and memory have millions of parameters, the controller has only 867. That's less than the number of words in this section of the script. So the controller is just a simple rule that takes two inputs, the current compressed sketch from the eyes and the current state of the memory, and outputs an action. Turn left, accelerate, brake. Why make it so small? Because the whole point is that the complexity lives in the world model, the eyes and the memory. If the world model does a good job of understanding what's happening and predicting what's coming, then deciding what to do becomes almost trivial. The hard part is understanding. The easy part is acting. This, by the way, is exactly what Lake and colleagues predicted in episode 1. They said intelligence is about building models, and once you have a good model, using it to act is straightforward. So how do you train this thing? So the first step is to let the AI drive randomly. Just mash buttons, go left, go right, accelerate for no reason. It's terrible driving, right? But that's the point. It's exploring the environment, collecting thousands of screenshots and actions that produce them. The second step is training the eyes. Take all those screenshots and teach the VAE to compress and reconstruct them. After this step, the AI has a visual vocabulary. It knows how to summarize what a racing track looks like in 32 numbers. The third step is to train the memory. So you take the compressed sketches and the actions and teach the recurrent neural network to predict what sketch comes next. After this step, the AI has a sense of cause and effect. So if the road curves left and I steer right, I'll go off the track. The fourth step is to train the tiny controller. So now and only now do you tell the AI what the goal is. Maximize your score. Stay on the track, go fast. The controller learns the mapping, giving what I see and what I expect. What should I do? So, and it works on the car racing environment, a top-down racing game with randomly generated tracks. This system became the first known solution to actually solve the task. It scored 906 out of a possible 1,000, beating every previous deep learning approach, many of which used handcrafted features like edge detection and LiDAR-like sensors. So the world model scored higher than all of them, and its decision-making component was just 867 numbers. Okay, here's where the paper goes from impressive to genuinely strange. Remember the memory model. M is a prediction machine. Give it a current state and an action, and it generates a prediction of what comes next. Then you can feed that prediction back in as the new current state and predict the step after that, and the step after that, and the step after that. Do you see where this is going? So you can unplug the AI from the real game entirely. Throw away the actual environment. Instead, let the memory generate the environment. The AI is now driving inside its own imagination. So they literally did this. They took the trained world model, disconnected it from the game, and let the memory hallucinate an entire racing track, frame by frame, turn by turn. Then they put the controller inside this hallucinated world and let it practice. And it could drive. The dreams weren't perfect, of course. They were blurry, a bit wobbly, occasionally surreal, like the AI version of those half-remembered dreams you have where everything is almost right but slightly off. So the road texture shifted, the colors drifted, sometimes the track did something weird, but the essential dynamics were there. Turns still curved. Going off-road still felt different from being on the track. Acceleration still moved you forward. Then they went further. They tried a completely different game, a first-person shooter called V's Doom, where monsters fire projectiles and you have to dodge them to survive. They trained a world model on this game, and then they trained an agent entirely inside the dream. The agent never saw the real game during training. It only lived in the AI's imagination. When they put this dream-trained agent back into the actual game, it worked. It could dodge fireballs and survive far longer than the required benchmark, even though it had never experienced the real game. It learned to survive in reality by practicing in a dream. Think about that for a moment. Now, I wouldn't be honest if I didn't tell you about the weird part, alright? Because this is where the story gets philosophically interesting. The dream wasn't a perfect copy of the real world. It was a model, an approximation. And the AI discovered that it could cheat its own dream. So in the V's Doom experiment, the agent figured out that if it moved in a certain way, the monsters in the dream world would just stop shooting. The fireballs would flicker into existence and then vanish. So the AI had found a glitch in its own imagination, a place where the dream broke, and it exploited it. It's like if you were lucid dreaming and you realized that the dream monsters couldn't hurt you if you stood in a specific spot. Great for dream survival, useless in the real world. So the authors call this cheating the world model, and it's actually a deep problem. It's deeper than that. It's really a deep problem. When you train an agent inside a simulation, the agent doesn't just learn to do the task. It also learns to exploit every imperfection in the simulation. So if the model is wrong about some part of the physics, the agent will find that weakness and abuse it. Their solution was clever. Again, remember how the memory module doesn't make a single prediction. It generates a spread of possibilities. They cranked up the uncertainty. They made the dream harder than reality. Fireballs moved more randomly. Things were less predictable. The dream world became a kind of nightmare difficulty mode. The agents that survived this harder dream turned out to perform better in reality. A model trained in easy dreams, where uncertainty was turned way down, scored 193 in the real game. A model trained in harsher, more uncertain dreams scored 1092. The same agent that was tortured by unpredictable dream monsters became the best survivor in the real world. There's a lesson in there somewhere. So let's zoom out and talk about why this paper matters, not just for 2018, but for everything that came after. Now, before this paper, the dominant approach to training AI agents was model-free reinforcement learning. That's what we talked about in episode 1 with DQN playing out Atari. The agent interacts with the real environment millions of times, slowly adjusting its behavior based on rewards. No model, no imagination, just trial and error, over and over and over. Ha and Schmidhuber showed something different. They showed you could separate understanding the world from deciding what to do. First, learn a model, then use the model, and once you have the model, you can do things that model-free systems can't, like practice in imagination, or learn with far less real-world experience. This was the proof of concept that the world models movement needed. Lake and colleagues had argued theoretically that AI needs internal models. Ha and Schmidhuber showed it could actually work. The ideas weren't just plausible, they were practical, and the influence was immediate. This paper directly inspired a whole lineage of research. The Dreamer family of algorithms, which we'll cover next episode, took this idea and scaled it up. Training agents in imagined worlds to play Minecraft, control robots, and navigate 3D environments. Muzero 2 at DeepMind showed that an AI could learn the rules of chess and go entirely from its own internal model without being told how any piece moves. And the DNA of this paper runs straight through to what Yann LeCun is building today. So when LeCun talks about learning abstract representations of the world and making predictions in representation space, that's the V module. When he talks about a world model that predicts future states, that's the M module. When he talks about a small planner that uses the world model to choose actions, that's the C module. So the 2018 World Models paper didn't just demonstrate an idea, it established the template that the entire field is still using. Let's connect the dots now. In episode 1, Lake and colleagues made the case AI needs to build models of the world, not just recognize patterns. Human intelligence runs on internal simulations and mental models of physics, psychology, causation that let us learn fast, generalize broadly, and imagine possibilities we've never experienced. Now, today we've seen the first real system that actually does this. Ha and Schmidhuber built an AI with 3 parts: eyes that compress the world, a memory that predicts the future, and a tiny decision maker that acts on those predictions. They showed it could learn to drive, learn to dodge, and most remarkably, learn entirely inside its own dreams. But this system was also limited. The dreams were fragile. They worked for simple 2D games, but they broke down in complex environments. The agent could cheat its own imagination, and the world model only predicted one step at a time. It didn't plan in any deep sense. It reacted to predictions rather than reasoning about long chains of future consequences. So the next breakthrough would come from researchers who asked, what if the AI didn't just predict the next moment, but imagined entire trajectories into the future? What if it could think ahead, not one step, but 50 steps, 100 steps, and pick the path that leads to the best outcome? That's planning. That's imagination with purpose. And that's what Dreamer and Muzero achieved, which we're going to be talking about in our next episode on planning in imagination. All right, thanks for listening. And if this helped something click, then share it with someone who's curious about where AI is actually heading. I'll see you in episode 3.